So the LPC1500 is a new series of microcontrollers. As you can see here, motion control simplified. So it's been designed with motion control in mind. And the visual here, you can see the different types of application that we've targeted the 1500 to. So bottom left-hand corner is the inside of a washing machine. So large appliance is a key focus for us. Air conditioning in the center is another application using multiple motors. And then industrial factory automation is another segment that the 1500 is a great solution for. The agenda for the presentation today, first of all, I'm going to cover an overall introduction to the series and what the parts look like. I'm going to touch on some of the key features on the devices that make them highly suitable for motor control. Some discussion on applications and solutions. It's not all about silicon these days, so we need to provide software, firmware, and the tools to get you up and running quickly. So we'll touch on that. Finish up with an overall summary, and then we'll have a quick Q&A session at the end of the webinar. So the LPC1500, the tagline here is flexible, fast, and simple. So flexible because many of the peripherals on the device are programmable, highly programmable, giving you the flexibility that you need to design your application. Fast, we're providing example firmware that will allow you to develop your own application faster and get you to market quicker. And then we're trying to make it simple as well. We're providing a GUI for motor tuning. So again, helping you speed your development cycle up. Other few points when we've been discussing with customers is that they have to drive various different types of motors depending on the application. So whether it's brushless DC, AC induction, or permanent magnets, synchronous motors, the 1500 is capable of driving all of those types of motors. The other problem that some of our customers had was driving multiple motors at the same time. You know, from talking with customers, they're using a single microcontroller to drive a single motor. But the key thing about the 1500 is because it has 28 PWMs and 24 channels of A to D converter, is capable of driving multiple motors simultaneously. And then, you know, a lot of customers have been saying that it's really difficult to tune the motors because each motor has individual characteristics, different inductance, different resistance, depending on the number of poles, the windings of the motor. So we created the GUI tool to make it tuning a lot easier. Regarding the application spaces, I kind of touched on it on the first slide. But in the consumer space, we see a lot of traction in large home appliances. In the commercial, it's on the air conditioning, elevator control, escalator control. And in the industrial space, as well as factory automation, driving large pumps and generators. But the 1500 is you know, it's an excellent part. It's not just dedicated solely to motor control. I'm seeing various different applications ranging from digital power supplies, data loggers, remote sensing applications, even to GPS and battery charging applications. So it's a very flexible part, and it's got a great feature set on there, so it is capable of doing multiple different types of applications. In this table, I've tried to highlight the different types of motors available, the different types of control, be it sensored or sensorless, different applications, and the hardware blocks on the device that make it suitable for the different type of control. I'm talking about the firmware and the GUI that we provide and overall benefit to end customers. So if I start with permanent magnet synchronous motors, those, along with brushless DC, both have censored and sensorless control methods that can be used with them. AC induction is typically censored because it's more heavy-duty load that's been driven, so more security is needed, so censored makes more sense. The hardware blocks on the 1500 that make it suited to sensor control typically is using the quadrature encoder interface. So this block connects directly to the QEI or Hall sensor on the motor. If it's using sensorless, we have a 2 mega sample per second A to D converter on the parts, 12-bit, 12 channel, and we have 2 of those A to Ds so that you can simultaneously measure currents in both of the legs in the feedback of the motor. And then for safety, we have 4 fast comparators on the part, which allow you to shut down the PWMs upon a fault condition. Regarding the firmware that we provide a brushless DC code that is freely available. The source code is freely available, and we have an application note around that. Likewise, we have field-oriented control for both censored and sensorless, and again we have the code and an application note available. The GUI, as I mentioned earlier, we have that to assist with the motor tuning. An overall benefit of using FOC control particularly is that you get low torque ripple, very precise speed control, improved motor efficiency, and low audio and electrical noise. So benefits to the end customer regarding power consumption and audio noise, which is particularly important in large appliances. Moving on to the block diagram of the 1500. At the heart of the device is an ARM Cortex-M3. It runs up to 72 MHz. There's 256K of flash with 36K of RAM, and also some EEPROM on there, 4K bytes. But the key things are in relation to the peripherals and the hardware interconnection between the ADCs, the comparators, and the SC timer PWM blocks, as well as the quadrature encoder. So those are the key blocks on the part for motor control. So the PWM can, when it starts driving the motor, can also trigger ADC conversions, so that you're getting simultaneous currents and voltages as the motor starts turning. And likewise, the comparator can shut down, is connected to the SC timer PWM, and that can shut down the PWM when the fault condition is detected. But there's a whole host of different peripherals on there. We have CAN for communication, industrial communication. We have USB, maybe for in-field upgrades or for data logging type applications. And the whole host of serial connectivity, I2C, UARTs, SPIs. And on the analog side, we also have a DAC, 12-bit DAC on there. So the other thing is regarding the algorithms that we provide. For the FOC, it only takes up 11K of flash. So we'll run in all of the parts, very small code size, and it runs in 40 microseconds. So it's a very tight loop for that motor control application. Regarding positioning within the NXP portfolio, the LPC 1500 fits in between the LPC 1300 and the LPC 1700. All of those are Cortex-M3 based products, and we do have motor control solutions based on the LPC 1700 and the ARM 7 and ARM 9 parts in the portfolio. But the 1500 has really been optimized to be a more efficient motor control solution. So touching on some of the key features on some of the peripherals on the LPC1500. The first one is the switch matrix. So the switch matrix allows you to route any function that's internal to the part out to any of the pins. There's a couple of exceptions that are hardwired, but those relate to the USB and the I2C pins. But apart from those, all of the other functions can be routed to any of the other pins. So the benefits of this are that every pin on the device can be used, every function can be routed out, and it simplifies schematic and layout when you're creating your board. The other things, you can dynamically change the functions on the pin, so you can configure it to be one function, and then as you're running, you can change the code and change the pin function. So again, giving you a bit of flexibility on the way that you want to design your application. Okay, so we also have a switch matrix tool, which is a graphical tool that allows you to select the functions that you are looking for. So again, trying to make things easy for customers and making a simple tool that the customers can use to assign the pinout. And that can be downloaded from our engineer to engineer site, LPCware. The next peripheral is the SC Timer PWM, and this is a typical timer that can do all of the input capture, output compare, PWM generation, but in addition it has a state machine attached that allows you to create different states and events to control the output waveforms or functions that you want to design. So depending on the event, whether it's an input or an output that happens, you can configure the way you want to control the counter. So you could reset the counter, you could continue counting up, or you could start counting backwards, and it allows you to create different types of waveform. It gives you more precise control over that PWM generation. So the key points are listed below. So for the 1500, there's 4 SC Timer PWM blocks. So that allows you to have up to 8 different timers. There's no CPU intervention, so actually our brushless DC motor control is done solely by the SC Timer PWM block without any CPU intervention at all. So again, if you were just controlling a brushless DC motor and you were wanting as low power consumption as possible, you could actually shut down the core, put it to sleep, and the SC Timer would control that motor independently. Each of the 2 counters, so the counters on the SC Timer PWM block can either be 1 32-bit or split into 2 16-bits, and they can operate independently and on different time scales. So again, giving you some more flexibility. You have full control over the resource allocation. There's no hardwired modes, and state machine allows for a whole host of different sequences and events that you can program. And again, we provide a tool, a graphical tool that allows you to program that state machine the way you wish. So on the 1500, there's 2 large state configurable timer PWMs and 2 small ones. The main difference is in the number of inputs, outputs, states and events, but also the larger block has the dithering feature, which allows you to get more precise resolution over your PWM. So as Mahesh, do you want to explain a little bit on dithering?
So you can increase your average PWM resolution over a PWM cycle of 16 PWM cycle by using dithering. Dithering can be useful in some of the applications like lighting application where you need high resolution, and you can have a average PWM resolution over 16 PWM cycles less than 1 nanosecond. That way you can have a gradual light increment, illumination increment with the dithering. So this is one of the feature available on our large SC timer PWM blocks. So we have 2 large SC timer PWM blocks in fact, and 2 small. So the large one, both of them had this feature available.
Thank you. Okay, so this is an example of using the SC timer to create the PWM. So the dots on the sawtooth waveform are where the match events happen. So as the counter counts up, you get your first match and you toggle the edge on your I/O output. And on the second dot, and a similar thing happens, you get your second match and you toggle the pin. On the right hand side, there's a center aligned PWM creation. So in this case, you're using the counter to count up and then count back, and on the matches you do the pin toggle. So it's very flexible, and it's you can define the system the way you wish to create the output waveform that you want. Moving on to the A to D converter. If you look at this, there's 2 A to D converter blocks on the LPC1500, both 12 channel, 12-bit, running at 2 megasamples per second. So the feedback we've had on the ADCs is they're very fast and they're very easy to use, and it allows you to capture the currents in the legs of the phases very easily. So we've had some good feedback on the ADCs on the 1500. So as I mentioned earlier, you can trigger ADC conversions via different inputs. So that can be from the SC timer PWM, or from a pin, triggering a pin, or from the comparator output. So there's various different options on how you can configure the ADC as well. So again, making it flexible. You can also create interrupt requests or DMA transfers or SC timer triggers as well. So just an overview of how we connect the 1500 in a system when we're driving the motor. So we have the SC timer PWM outputs that are driving the gates of the FETs to drive the motor, and the current feedback in each of the phases goes fed back into the ADCs, and also you can measure for overcurrent. So the comparators, there's 4 comparators on the 1500, 7 different selectable inputs. So again, on the configurability and the flexibility of the part gives you various different options. The temperature sensor can be selected either on the positive or negative of each comparator. So if there is a problem in the system and there's an over temperature condition, then the comparators can shut down the PWM. So the individual comparators can be connected for the ADC trigger, and there's 3 propagation delay settings depending on power consumption and the speed that you request. The quadrature encoder interface is a hardware block which provides pulse outputs, and depending on the number of pulses and the phase between the pulses on QEA and QEB, you can determine the position, the speed, and the direction of the motor. And there's also an index signal that if you want to reset the position counter, then that can be done also. And any of the QEI pins can be selected or movable in any case using the switch matrix. So again, flexibility. So looking at the different applications that I mentioned previously, so if you're wanting to drive multiple motors simultaneously, in this example here we're driving a brushless DC and in sensor mode and FOC motor in sensorless. So the benefits here is reduced time to market using the firmware that we provide. Obviously customers have their own IP that they want to put in their application, but we just want to provide an environment where customers can take what we have and adapt it to suit their needs. So it gives them a starting point to start their development. The FOC control firmware allows you to have very smooth, quiet and efficient motor drive. And as I say, you can control 2 or more motors simultaneously using the 1500. And as you can have a safe system shutdown using the comparators for detecting overcurrent. So examples of that would be driving multiple motors would be in an HVAC system where you have to drive the compressor, which is typically a permanent magnet type motor, and driving the fan at the same time, which is typically a BLDC. So we'll be using the SC timer PWM block to do the driving, the ADC for collecting the feedback, and also the temperature, if there was an external temperature sensor, we do the conversion there. And then if it was connected, communications could be done via CAN or USB. Similar situation with a large appliance. So for example, here we have a dishwasher. So the SC timer PWM would be driving the dishwasher spray arm and the water pump. And again, the ADC collecting looking at the feedback in the system from sensors or directly from the motor itself. Power supply is another example. Because the control loop is very similar for digital power as for motor control, so rather than driving the motor itself, the PWMs are driving the FETs that control the output voltage and current, and the ADC is obviously monitoring the output to make sure it closes the loop and you maintain precise control over your output voltages and current. So again, similar features needed to drive that type of application. And again, if there's any fault conditions, the comparator can shut down the output PWMs. Touching on a couple of the solutions that we have. So it's not just silicon. We're not just providing silicon and typical evaluation board. We provide motor control kits, one on permanent magnet synchronous motors and one on brushless DC. Both use the same motor drive board, the base board, but both the output stages are connected to the different type motors, so and different algorithms are provided to drive the boards themselves. So we provide the firmware, we provide the GUI to go along with this, we provide the application note, so it's a complete solution in a box. And the brushless DC version is pretty similar, just a different type motor, the BLDC motor provided along with the same base board and the LPC1500 board. So regarding software and tools, along with the silicon obviously, we provide LPC Open, which provides low-level drivers for each of the peripherals. On top of that, we provide board support packages and middleware, so USB stacks and the CAN Open stack. And on top of that, we have our own development environment, the LPC Expresso. So it's code environment to allow you to compile and link and download your code onto the device. We also have embed prototyping, and we support third parties as well. So it's not just LPC Expresso, its our own its KEL and its IAR as well support. Okay, so the key point in this slide is for LPC Expresso, we have a download limit of 256K. So on the LPC1500, there is only 256K flash. So the point here is that you're getting free tools. So there's free tools available, so there's no cost involved in starting to develop with the LPC1500. However, if you do wish the full supported edition and the Pro edition, it's less than $500. So it gives you full support for the full tool chain. If your application does not have motor control, then you're just looking for an evaluation board to look at the LPC1500. We do have a separate board. It's our own LPC Expresso, and this board is it's very flexible. It has the embed and the Arduino connectors on there. So if you want to build a little system up using the Arduino shields, then you can do that very easily. And these boards are pretty cheap. They're in the less than $30, so it allows you to start evaluation pretty quickly. The other key point is they have an onboard debugger. We have the LPC Link 2 on board, so there's no need to buy a more expensive debugger to plug into the board. So in the series itself, we have a list of 13 different part numbers. Some have USB and some without, and they come in various different memory sizes and package sizes. So ranging from 256K flash down to 64K, and ranging from 100-pin package down to 48-pin package. So there are various different options that, depending on your needs, you have the selection there. This is just some boards and tools information. So if you are interested in evaluating the part, we've got a list of the board part numbers and where to go and access more information on those parts and boards. So typically you'll find it on nxp.com and lpcware.com. For support, NXP obviously is the website to go to first. Along with LPCware, you can download the code for the motor control kits, and you can get access to schematics and any libraries, application notes, anything you need on LPCware. And there's also links to technical support if you need further assistance. So to summarize, the LPC1500 is great for driving various different types of motors, not just one dedicated type of solution. So you can drive brushless DC, permanent magnet synchronous motors, and AC induction. It can drive multiple motors simultaneously, and you can do it either sensored or sensorless. So you can use the QEI, or you can just use the ATDs and the PWMs. The combination of the firmware that we provide and the GUI should simplify your development and help you get to market quicker. The hardware interconnection between the SE timer PWM, the ADC, and the comparators help to improve the performance of the PID control loop, and that runs in 40 microseconds and only takes up 11K of flash. Various different target applications that we see the 1500 suitable for: large appliance, air conditioning, factory automation, digital power supplies, remote sensing. So even if you don't use motor control, 1500 is still a good part to use in different applications. And LPC 1500 is cost-effective motor control solution. So if we compare it to the competition, we know the pricing is very attractive. So I'd like to thank you all for taking the time to listen to me today, and I'd like to open up to any questions. So we have one question here. Why do you tune a motor? Do you need to individually tune every motor that's shipped? Well, the answer to that one is yes, because each motor has different resistance and inductance, different number of windings, so every individual motor has to be tuned. Are there any trade-offs while using the SCT PWM less than 1 nanosecond? Do we have sample code that demonstrates the dithering feature? I'll let Mahesh answer that one.
Yes, we have a SC timer PWM cookbook available on lpcware.com, where we have one example which shows the dithering feature available on LPC1500 large SC timer PWM blocks.
Okay. Another question is, on the LPC1500 diagram, isn't there supposed to be a temperature sensor in the analog block? So the answer to that is yes, we do have a hardware temperature sensor in there. Okay. Okay, other questions coming in? Let's see. Can I ask a question to the organizer? How do I expand the questions so I can see them?
You can drag the box just like you do any other window.
Okay. But I only see a very small window. That. Okay. Is this device as robust as the LPC122X when it comes to EMI, EMC specifications? Nash, you want to answer that? So the output structures, so the structures of the pads have been improved over the years, so they should actually be better than the LPC1200. Okay. Any other questions? What ratings of the motor in terms of per RPM does the LPC1500 support? So it's really dependent on, I'll let Mahesh answer this, but it's really dependent on the motor drive board that you design. So the 1500 can drive any type motor, any power rating. It's really up to the power stage design. I'll let Mahesh answer that.
Yeah, so the SC timer PWM block in LPC1500 operates up to 72 megahertz. So you can clock the PWM block at 72 megahertz. So you can generate a high PWM, and if you are operating a BLDC motor, in that case your state switching will be happening in the hardware, so it will be very fast. So you have two loops, the inner loop, which is actually the state switching loop, which will be happening in the hardware, so you can go up to very high speed. The other loop, PID loop, it depends on the algorithm, which kind of algorithm you are using, and the core is operating at 72 megahertz. So based on that you can calculate how fast you can do the PID algorithm at outer loop. But definitely at the inner loop, in case of BLDC, you can use hardware, which will be very quick, as the PWM block is operating at 72 megahertz.
Okay, so I have another question. Can both OM 13068 and 67 kits be used for sensorless motor control? The answer to that is yes.
So we have a common board that is called motor control board. We developed that motor control board with embedded artist, and it has facility to control sensorless brushless DC motor as well as the PMSM motor. So you have comparator connected to the motor control board to the LPC1549 espresso board. The ADCs are also there. So if you see, you can control a brushless DC motor in sensor and sensorless mode, because the Hall sensors are also directly connected to the microcontroller. The other is the QI is also connected to the microcontroller, and the ADCs are also there. So you can do virtually any sensor or sensorless mode control in case of PMSM as well as the brushless DC motor.
Okay. So another question, what if I want to use a different motor than the one in the kit? Can I use the same hardware and software? So the answer to that is the board can only drive a certain wattage of motor, right? So the EE board can only drive up to 24 watts.
Yeah, so in this particular board we have adapter which can deliver you right now at 1.5 ampere and 24 volt, which comes around like 24 VA. So right now with that adapter you can go there up to 36 VA, but this particular board has MOSFETs which are actually can drive up to 100 ampere each. Those are NXP MOSFETs, and there are some current tripping as well. So you have to adjust current tripping in the motor control board to set your current what you want. But the MOSFETs are capable of driving up to 100 ampere. So basically you need an external supply, your own supply, which can be used with this board, because the MOSFET part is capable of driving high load, and you need to set the tripping point where you want to trip the bus current.
Okay, another question is, what's so special about the way the peripherals are interconnected? How does it help motor control? Is it unique to NXP?
So there is a lot of connection between A to D converter, PWM block, comparator, and there is another block which is called SCT IPU. So in case of PMSM FOC control, you want to trigger ADC at a particular time. To take care of that, there should be a synchronization between SC timer PWM block and ADC. So this particular feature, interconnectivity, actually and there is SC timer PWM block has an input unit called SCT IPU, which ensures when you want to take the input, and that is controlled by SC timer PWM block. So SC timer PWM block has a lot of flexibility to control various peripherals. Another control is coming from ADC blocks. ADC blocks have upper threshold and lower threshold detection, and it can trigger the SC timer PWM block, and based on that you can actually detect the high voltage or low voltage, and you can switch off the PWM. So there are lot of connectivity in this microcontroller, which will help you to control motor as well as the power supply applications.
Okay, next question. What are the benefits of having two sample and hold circuits?
So one of the control algorithm nowadays very popular is like DTC, direct torque control, and the FOC, field oriented control. And in field oriented control, you want to take samples of each phase current of the motor at the same time. So in our case, we have two separate ADCs. Each ADC is running at 2 megasample per second, and each ADC has 24 channels. For two phases, you need two channels, so you can use each channel from each ADC so that you can sample simultaneously and at 2 megasample per second, which will give you an accurate measurement. So FOC need, for example, in case of sensorless, you need an accurate measurement. In case of FOC algorithm also, you need an accurate measurement. So you can do using two ADCs here.
Another question is, how fast can the evaluation boards drive the motor in the RPM? So I think you've been running up to 6,000 RPM on the board.
So this case right now, we are using a Technic motor, Technic PMSM motor, which is going up to 3,000, because the Technic motor is drawing around 7.1 ampere, I think, at full load, and right now our power adapter is going only up to 1.5 ampere. So it's going right now at 3,000, this particular board.
Okay, so that's the OM1506.
Yeah, so this motor is an 8-pole motor, so I think there is a limit up to only probably 5,000 in this case. And if you have less pole motor, you can drive it faster with this board, but then the current should be limited by, I mean, it's limited by the adapter. So if you use bigger adapter, probably you will get more.
Can it support brushed DC motors? The answer is yes.
Yes. So brushed DC motor is easy to do, because brushed DC motor is a self-commutating motor, and you have brushes to take care of the commutation, which doesn't need a sophisticated electronics. We are talking about the brushless DC motor and PMSM motor, or AC induction motor, because those motors are not self-commutating motors, and we need sophisticated electronics for them. And in case of brushed motor, you just need to change the PWM width for the armature. Normally the PWM width for the field is fixed, so it's very easy to drive a DC motor, a brushed DC motor.
Okay. Do we have an app note that can help a customer connect a motor of his choice and get started in a short time?
Yes, so the kit has a starter document, and it tells that how to connect the motor, where are the phases, and we also have videos available on lpcware.com where it shows what to connect to where. So there are two connectors, one is for sensor and the other one is for motor on the motor control board, and that will be coming in the starter kit, as well as we have an application note available on lpcware.com which shows how to connect motor and sensors and how to use GUI as well. So there are two application notes right now. One is for brushless DC motor and the other one is for PMSM motor. So brushless DC motor application note shows the detail about how to control the brushless DC motor in states. So as I told in my previous discussion, that you can control the states totally in the hardware, because this SC timer PWM block is capable of doing that, and you can have an outer loop which could be the slow loop, which is the PID loop you can have in the software. That way you are controlling the faster loop in the hardware and we're not wasting the CPU time to switch states. The other one is the PMSM motor, where you do a lot of things in the software because you have the SV, PWM, and other sensing algorithm there. So that application node is also there. So all these two application nodes show how to connect and start the motor control.
Okay, so that's all the questions we have. I'd just like to thank everyone for joining the webinar today. And for further information on the LPC1500, please look at nhp.com or lpcware.com. Thanks again. Bye for now.